It's been a while since the last Amplifier Masterclass video, and today Florian and I are going to be doing an overview on a new option as part of K18 or K18M, which is the Memory DPD. And yeah, here we have it on screen. So Florian, what's different? What's different to K18, K18D that we talked about in the previous videos?
Hello, everyone. So the main difference between an algorithmic DPD and our direct DPD, the K18D thing, is that K18D obviously only exists as a waveform. So we have no clue whether this can be applied or the type of linearization can be realized in a real-world system. However, when we derive an algorithmic approach for the DPD, as we do in K18 with a polynomial, or as we do now with a memory polynomial in K18M, that's definitely a DPD that can be applied to real-world systems.
Okay, so what are the things that we're going to look at today? I guess similar to the previous K18 videos where we looked at the effect of the DPD on ACLR and EVM.
Before we do that, I want to speak quickly about a minor change in K18D. So why do we speak about this in conjunction with K18M? Very easy, because all the DPD stuff, the memory polynomials, they are derived from K18D. So K18D is a prerequisite to K18M, and you always have to run K18D first before you can apply or derive a memory polynomial DPD. Okay, so let's have a quick look at what has changed. So please note we're running a beta version of K18M today, so some things in the GUI are not final yet, but it all works as expected, and this is the main thing we want to show today. All right, so the difference, or what we changed, is for those of you who are into the details of K18D, you might figure, or you might see that the default value for the DPD power linearity trade-off is now 50%. It used to be 100%. So why did we change it? And what is the expected result of that change? In very short, as long as you keep it to the default setting, so now at 50%, you shouldn't observe any significant difference. So what is it all about then? I have a little graph here that explains the whole thing. Sometimes when speaking to a customer, if you're looking into literature, you might find the term gain normalization there. And this is pretty much what we're talking about. Most of you will know that we always had the 0% case of our linearity trade-off. 0% always meant make it perfectly linear. And how can we make it perfectly linear? Well, we have to decrease the gain, or we have to go to this line here, the orange one, which is sort of connects or uses the gain that we see at the highest input power up here. Because this is something we can maintain over the entire input power range. And when we speak of gain here, sometimes people get confused about it, but gain, as we use it, is always the comparison signal out, so measured signal against the original reference signal. Obviously, I cannot really change the gain at low input power levels. But what I simply do is, with my DPD signal, I bring less power into the device under test, meaning that the device under test outputs less power. And so when we compare to the original reference signal with the original reference signal power, RMS signal power, it means we see less gain, as we have less output power, but we keep the reference signal and power the same. So this is just an annotation to not get confused about the different gains that come into the game here. Okay, so the orange one is the 0% case. We've always had that, and it continues to be the 0% case. Now, if you look at the purple case there, this is what used to be our 100% case and is now our 50% case. So what is it? In the legend, it says it's the linearized waveform with the current average gain. So when you apply your reference signal with your reference power, we typically operate the device under test in a slightly compressed way. So the average gain over all input samples will be slightly less than the small signal gain. And well, as I said, that used to be our default setting. We used to call it 100%. We changed this to be 50% from now on. And it's sort of, well, a trade-off between keeping the output power constant and giving the algorithm a chance to really improve EVM and ACLR. However, there is another case with an even higher gain that can be used. That's the small or so-called small signal gain here in yellow. Obviously, that's the gain that we see with low power levels here. Also, obviously, we may not be able to maintain this gain up to here, but this is the ideal linearized case. And this is, or the intention of having this is, some of you may have noticed that when you are really compressing a device in a test with current K18Ds, you might see a decrease in output power. Now with these modifications, you can, even if the device is compressed heavily, you can keep the output power constant. The price, however, that you have to pay is obviously the linearization effect will not be as good as if you use the 50% case. Simply because the device is deeper in saturation or deeper in compression. That's in short a change for the power linearity trade-off. As mentioned, if you've never touched a parameter, simply keep on doing so and you should get the same results as before. However, if you're into that, you now have the chance to decrease the parameter as well as to increase it. And you should see an effect on the output power after linearization. Okay. Now, let's have a look at the new memory polynomial pre-distortion mechanism. I have prepared a setup here. It's an OFDM signal with 100 megahertz of bandwidth. I'm already using 5 times oversampled signals so that we have enough bandwidth in the signal to measure ACLR in K18, and obviously we need that bandwidth also in order to allow K18D to improve ACLR and EVM. If we recall the previous videos, K18D has to see the nonlinearities in the spectrum in order to be able to compensate for that. Okay, as you might also see, it's not compressed heavily, only slightly. I'll tell you later why I'm using this setting. Okay, what I'll do now is I'll simply start my Direct DPD. By the way, I'm using the default 50% setting. And as you can see, the output power stays constant because I'm in the, I would say, normal operating range without heavily compressing the device in the test. Okay. We've done some DPD. We've seen, surely we see increased, or I'm sorry, we see better EVM, decreased EVM. However, the ACLR itself, well, I think it more or less stayed constant. Okay, what we'll do is we'll go to Spectrum Analyzer and sort of copy the trace and keep it as a reference for later on. So the blue one is now our reference for K18D. So round about 42, 42.5, 43 dB ACLR and 1.6% EVM. Now in the measurement settings for DPD, we can see an additional tab for Memory Polynomial DPD. This is where I go into now. And you can see it's fairly easy to configure. It has basically 3 parameters. It has the iteration step that you want to use as the basis for the Memory Polynomial DPD. And then obviously it allows you to set the order, the polynomial order, and the memory depth. Let me quickly speak about this iteration step. For that, I'll turn off the DPD again, do a measurement, bring up the result window config, and what we can see is we have a new result window, which is called DDPD results. Per default, it's configured to show EVM over iterations. And I'm using my second one to show the ACLR. And by the way, since we turned ACLR off, we might take the chance and also save a trace in the Spectrum Analyzer for the nonlinear S case. Okay, let's start Direct DPD again. And now what we see here is we get EVM results over iterations. And for those of you who have some experience with K18D, typically it's decreasing over iterations, but every now and then we see slight increases. And in order to be able to use the best iteration, we have exactly this parameter where we can tell K18M the iteration step to use for the modeling. So as we see here, the 5th iteration is probably the best one. So let's take it. Per default is always the last iteration there, but we'll use number 5 here. Then for the polynomial and memory depth order, I just leave the defaults in there. Feel free to experiment there. Just note, the longer the waveform or the longer your test signal and the more memory depth and polynomial order you invest, the longer will be, of course, the calculation time. All right, so K18M is configured. Now I can say model. Takes a while, a few seconds. And then I get the other buttons enabled. And I guess what we want to see at first is how good is the result. So I can generate a waveform where I have applied the algorithmic DPD. Don't confuse it with the K18D, even though we get a waveform there. The waveform is generated by applying a memory polynomial DPD. But as the generator doesn't have any means of applying this memory polynomial DPD in real time, we have to apply it to the waveform. And obviously, I can also export my coefficients so that I can calculate the same type of DPD in my real world system. I just save the coefficients, and then we're going to have a look at the result. And now you might see something really interesting. For those of you who remembered the K18D, EVM, and ACLR results, you can see K18M results are better. How is that possible? This is fairly easy to explain. Basically, what we see is an influence of noise on the DPD waveform. So remember, in green, we had the original output signal of the amplifier. And then in blue, we had the K18D result. And we could see that, well, basically what happened is K18D filled up the adjacent channels with sort of noise. And interestingly, K18M is now able to compensate that. Or in other words, it simply means noise cannot be modeled by a memory polynomial. That's why it's not included in the K18M waveform. And of course, the big benefit is you'll get the coefficients for the memory polynomial model that can be applied, for example, in an FPGA in a real world system. At this point, we're more or less done with the K18M demo. However, looking at this graph, it looks a bit as if K18 was not able to fully linearize the signal. That's obviously not true. It just requires to, or I just have to make an additional setting to be able to get to these results as well. As I said, what we saw there was the influence of noise. So what we do, we just switch on IQ averaging. And then theory says we should be able to get pretty much the same result. So let's see. Takes a while, of course. That's the price we have to pay for the IQ averaging. We can already see the numbers approaching those from the previous K18M measurement. I'll give it one more iteration and then I'll just finish it. For the final measurement, we don't want the averaging. And we can see 45 dB and 1.2%, pretty much the same as we got with K18M. And also, if we look in the spectrum analyzer there, well, I probably should have waited until more iterations of the DPD were finished, but you can clearly see the trend. The shoulders or the out-of-band emissions are a lot lower than compared to the blue case where we did the direct DPD with just one, or basically without IQ averaging. So in short, or in a summary, K18M is, or gives you the modeling parameters. So K18M, or the result of K18M, gives you a pre-distortion algorithm that can be applied in real-world systems. And in addition, it can even speed up your direct DPD because it might save you from having to do a lot of IQ averaging.
Going back to the DPD results windows that you have on screen there, were those available with K18D, or is that something new as well?
That's something new as well, of course. The reason why we implemented it is simply because it makes it easier to pick the right iteration step of K18D for the modeling, because obviously you want to pick the best one that we had. As I said, typically that's the last one, but often when you get to the, well, to the very end, or when you have optimized it a lot already, then often you get some minor fluctuations. So this graph helps you to pick the right iteration step.
I think anybody that uses the K6, for example, would be used to this kind of view. It's like a parameter trend type view where you can look at a particular result and see how that changes on, capture to capture or run to run. And here we're just using that in the basis of, like, say, picking the best result, which you can then model and then export the data and use that to apply in your real world situation to your device later.
Correct, yes.
Wow, even I understood it. Nice. Okay, then I guess that's all for this video. And yeah, thank you very much again, Florian. Maybe we get an update when everything is fully released and good. And yeah, we'll go from there. Thank you very much.
Yeah, can for sure do that. Thank you.